Hello everyone, welcome to Instrumentation Measurement 2. I hope all of you are fine. Before the midterm, we started the flow chapter. Then we discussed the following item: the flow rate and the mass flow rate and the weight flow rate. Then later on, we discussed the continuity equation with the Reynolds number. And after we get the Reynolds number, is it laminar or turbulent or transition flow? Then finally we cover the Bernoulli equation, and we took one example to solve for the Bernoulli equation with the continuity equation. In today's lecture we are going to discuss the differential pressure elements, but before that we need to discuss the following items. What is differential pressure, and why, or what is the reason to choose the change in pressure as a principle for the flow measurement? Then later on we'll discuss the famous differential pressure elements and how to derive the ideal equation of a flow measurement based on the differential pressure. What is the differential pressure and why we need it? From the name differential pressure, we know that it is the difference in pressure between two given points. Why we need it? There are many applications that require the differential pressure measurement in order to measure the fluid movement. Those instruments, we call it the differential pressure element, are varying in their accuracy and their compatibility in producing a differential pressure. What is the reason for choosing the change in pressure as a principle for the flow measurement? We can simplify it by starting from the second law of Newton. Force equal to the mass multiplied the acceleration. We know that any fluid will contain a mass, and in order to move this mass we need an acceleration, and this acceleration will not happen without a force as per Newton's second law. And we need to consider the fluid as a one solid material moving inside a pipe, taking the cylindrical shape of this pipe as shown in the following figure. Here you can see that the force equal to the mass multiplied the acceleration. If we want to express it as a pressure, we can say pressure multiplied the area equal to the mass multiplied the acceleration. We already know from instrumentation 1 that the pressure equal to the force over the area, which is equal to the mass multiplied the acceleration over the area. So we can say pressure multiply the area equal to the mass multiply the acceleration. Then if we need to express the mass as a density multiply the volume, it will be the pressure multiply the area equal to the density multiply the volume multiply the acceleration. And if we divided the equation by the cross-sectional area, it will give us the fraction of the volume over area that leads us to the length between the two sequential points of the pressure before the shape and after it. So the pressure will be the density multiply the length multiply the acceleration. Now in this slide we are going to discuss the famous differential pressure elements. A very common way to cause a linear acceleration in a moving fluid is to pass the fluid through a constriction in the pipe, thereby increasing its velocity and also the pressure in the inlet of the element. We call it the upper stream of the element. Is most of the time the high pressure side, and the pressure in the outlet of the element downstream of the element is the low pressure. We are going to see it in the following figure. In figure 2, we are going to see 5 pressure differential elements: the Venturi tube, the flow nozzle, and the orifice plate, the mostly common used one, and the V-cone and the segmental wedge. All of them have the same principle. The liquid will come, or the fluid will come from the inlet and will pass through the construction area, then it will go out from the outlet. Now as you see in the figure, there will be a linear change in the acceleration. This will cause a change in velocity and change in pressure. We will get high pressure in the inlet and low pressure in the outlet. Another way to measure the differential pressure is by mounting the differential transmitter at an elbow. The acceleration fluid will force to be turned at a corner in the pipe fitting. We call it the elbow. This will generate a radial acceleration, causing a pressure difference between the outside and the inside of the elbow. It means the internal turn and the external turn of the elbow. This will cause a differential pressure. We can measure it through the differential transmitter. Note the following. Those previous elements are causing the differential pressure by accelerating the fluid. We are going to see in the next slide another instrument that will use the deceleration to measure the differential pressure. In this slide you can see that those differential pressure elements work with the deceleration. The first one is the beta tube and the averaging beta tube and the target tube and the anabar tube. Here we can see the opposite of the previous differential pressure element. Here we have a deceleration. It means we have decrease in velocity, and the lower pressure will be at the inlet and the higher pressure will be at the outlet. And note that all these differential pressure elements are either working by accelerating the velocity of the fluid or by deaccelerating the velocity. It can work in the same principle. Both types give the flow measurement by developing the difference in the pressure between the both sides of each element. Okay guys, in order to derive the equation of the flow rate according to the principle of the change in the pressure due to the movement of the fluid, there are conditions to be applied for this purpose to make it simple. We will discuss those conditions in the next slide, but it is good idea to take the conical shape of the derivation. It is usually used in the book the Venturi tube for the derivation. The condition we mentioned in the previous slide are the principle of the energy conservation will be applied in the Venturi tube to derive the relation between the flow and the differential pressure. Also, the Bernoulli equation will be used for this purpose in order to let our equation to be near to the accuracy and simplicity as possible as we can. We should apply the following condition in the Bernoulli equation. No energy lost or gain in the Venturi tube. No mass lost or gain in the Venturi tube. Fluid incompressible to ensure the stability of the pressure value between the 2 points. Venturi tube center line is level. In the next slide, we are going to see how we can change this Bernoulli equation to the following equation, the flow rate equation. Okay guys, based on the previous condition, the Bernoulli equation can be used in the ideal form. The pressure 1 plus rho gh1, which is the potential energy, plus half rho v1 square. V is the velocity and this is the kinetic energy, equal to b2 plus rho gh2 plus half rho v2 square. We know that the h1 and h2 are the elevation head at point 1 and 2 respectively. Those elevation head are equal, so they will cancel each other. So we are going to cancel the potential energy from both sides of the equation. And the density is the same in both points, so the density can be taken as a common factor. The resultant Bernoulli equation will be as follows. Now guys, based on the first condition and the second condition, the principle of the energy conservation can be used in finding the flow value. The flow is counted as per the continuity of the mass equation. The flow rate equal to the velocity at point 1 multiply the cross-sectional area at point 1 equal to the velocity at point 2 multiply the cross-sectional area at point 2. So it is possible to find the relation between the two velocities in both points as shown in the following equation. Either we can say V1 equal to cross-sectional area 2 divided by cross-sectional area 1 multiply the velocity at point 2, or we could say if we need to find V2, equal to the area or the cross-sectional area at point 1 divided by the cross-sectional area at point 2 multiply the velocity at point 1. Now from those relations we can apply the following equation by using V1 equal to the cross-sectional area 2 divided by the cross-sectional area 1 multiply the velocity at point 2. You will see the equation became like this, the resultant Bernoulli equation. Half multiply V2 square minus area 2 divided by area 1 multiply V2 all square multiply the density equal to B1 minus B2. Now we will take the V2 as a V2 square as a common factor. The final resultant equation will be half V2 square multiply open bracket multiply 1 minus area 2 over area 1 all square close the bracket multiply the density equal to B1 minus B2. Before we continue driving the flow rate equation, you need to note that the two cross-section area A2 and A1 are area of circle with the diameter of the pipe at point 2 and point 1 respectively. The relation between those 2 points can be transferred to the relation of the diameter of both points located inside the pipe as shown in the following formula. A2 over A1. We know that A2 is the area of circle is 1 over 4 by D small square. So for area 2 we will use D small and for area 1 we will use D capital. Now we will remove 1 over 4 by from the numerator and the denominator, so we will get D small square over D capital square, or we could say D small over D capital all square. Now after we change the relation of the cross-sectional area to the relation of diameter, whereas D small and D capital are the diameter of the pipe at point 2 and point 1 respectively. The diameter of the pipe at point 2, D small, is called the diameter of the throat, and the diameter of the pipe at point 1, D capital, is called the diameter of the mouth. So it can be substituted in the equation as shown in the following formula. Half V2 square, then we open a bracket, 1 minus bracket, another bracket, D small over D capital, close the bracket, it will be squared, all squared. Then we close the bracket again, all squared, then close the bracket, multiply the density equal to B1 minus B2. Now we need to change V2 square. We know from the continuity of mass equation the Q equal to V2 multiply the cross-sectional area 2. So if we need V2 square, it will be Q over A all square. So the final equation will be half Q over A2 all square, another bracket, 1 minus D over D capital, close the bracket, to the power 4 since it is a squared square, then we close the bracket, multiply the density equal to B1 minus B2. In this slide, by rearranging the previous formula, we are going to see the final or the resultant formula in 2 steps. The first step will be Q square equal to B1 minus B2 over density multiply 1 minus D small over D capital all to the power 4 divided by 2 area 2 square. The next step, it will be Q square. We know that the denominator of the denominator will be numerator. So 2 multiply A2 to the power 2 multiply B1 minus B2 over 1 minus D small over D capital to the power 4 multiply the density. Now after taking the square root of both sides of the equation, it will give you the following form. I will show you in 2 steps. The first step will be Q equal to A2 multiply square root 2 multiply 1 over square root 1 minus D small over D capital to the power 4, all of them, then multiply by square root B1 minus B2 over the density. The next step or the resultant step will be Q equal to by D small square over 4. This is the area of this cross-sectional area. Multiply square root 2 multiply 1 over square root 1 minus D small over D capital all to the power 4 multiply square root B1 minus B2 over the density. Now we can express d small over d capital as a beta ratio. So beta equal to d small over d capital. And the difference between the two pressure points can simplify it as delta P. Finally, the resultant equation will be in the following form. Q equal square root 2 over 4 multiplied by d small square multiply 1 over square root 1 minus beta to the power 4 multiply square root delta P over the density. It can be simplified in the following ideal form, which show the relation between the flow measurement and the differential pressure between two effective points of a primary element. We will discuss what is the K in the next slide. In the previous slides, we have found the flow rate equation, which is Q equal to the K multiply square root delta B over the density. In this slide, we can see what is K. K is equal to square root 2 over 4 by d square multiply 1 over square root 2 1 minus beta to the power 4, or we could say it is the unit correction flow factor. This flow rate is for the volume per the time. In order to find the flow rate by the mass over the time, it can be taken by the following equation. Qm equal to the density multiply the flow rate equation. So if we rearrange the equation, it will be, or if we multiply by the density, the flow rate of the mass can be expressed in the following formula. Qm equal to the K multiply square root density multiply delta B. How come it became like this? We know if we multiply the flow rate with density, we will put the density under the square root as the density square, and one of the square of the density will go with the density in the denominator. So we will get this form. Okay guys, we will stop here. This was part 1 of the differential pressure element, and we will continue part 2 as soon as possible, and I will send you the information in the blackboard. The summary of today's lecture was: what is the differential pressure, what is the reason for choosing the change in pressure as a principle for the flow measurement, and we discussed the famous differential pressure element and how to derive the ideal equation of flow measurement based on the differential pressure. If you have any question, you may ask me through the email. Thank you. Okay guys.